Dr. Rob Masserini. He is now at the University of Tampa, where he is an associate professor and chair in the Department of Chemistry. And he has a great talk for us today on nutrients and ammonium analysis.
I want your applause. We're going to wait on that. So, till we see the story, right? I was thinking to myself, it's been 18 years since I've been in this room giving a talk. So it's really nice to see the change and to talk to some folks and see what's been happening here. So since I don't know very many of you, my name's Rob. I'm a Capricorn. I like taking long walks uphill, carrying heavy things. And I have a penchant for doing like really masochistic things, like climbing El Capitan and hauling hundreds of pounds of gear up with me afterwards. And the reason why I tell you that is because you probably share some of those masochistic tendencies as well. Because when I was here, I spent a lot of time like building the sensor systems and on this thing. It was a autonomous underwater vehicle, and it had underwater analysis system to detect nanomolar concentrations of nitrate, nitrite, and ammonium. So I worked with the engineering group here extensively. And when I gave my PhD defense in this room, I told everybody, don't do this, right? You know, and that I should have had a helmet for the amount of time that it took. And it was kind of a learning experience, but I was kind of fortunate that I could take that technology and repackage it. And put it in a smaller platform. And so Hannah's not with us, but she was a co-author with me on another paper that I'm going to talk a little bit about today. But she and I used that. We took the instrumentation that was here and put it into a smaller package. And now we can put it on just about any vessel. And I'm fortunate to have the option to use the RV BIOS, which is the University of Tampa's larger sport fisher. It's 46 feet long, and we can install this. We see my one student here inside the lab, and we can take this tow it behind the boat, pump the water up to the system, and we can map ammonium in real time, essentially, in Tampa Bay. And I'll show you some data from this particular cruise. One thing, we had a bunch of biologists in the room, I take it. That usually is. Yeah, no, yeah, I say, Claire said it is. Like, when we got on the boat this time, and I had a bunch of students who volunteered to help me, they were like, this thing has air conditioning. We've been going on this for years, and they never knew it had air conditioning. Like, being a chemist, I was like, we're going to turn the air conditioning on. We're going to control the temperature. We're going to control kinetics. We're going to control exchange rates and equilibrium constants. Please, we want to do some precise work. So we did. They were very helpful, though. I have to say that. I had them count, the biologist. All right. So I would feel a little remiss. And I think Lavoisier would be turning over in his headless grave if I didn't at least write a few chemical reactions. And I know the trace metal people, relax, don't get your knickers in too much of a twist here, right? This is the nutrient chemist view of photosynthesis, right? Where we have some nitrate, or in this instance, ammonium, because I'm going to talk more about ammonium today. Ammonium and phosphate in the form of phosphoric acid combining with carbon dioxide and water to give us some organic material and release energy. I had a student just on Wednesday ask me, well, how important are nutrients? I said, well, do you like breathing? Right? And he's like, what do you mean? I said, well, you know, the surface ocean gives us about half the oxygen on the planet, right? So maybe every other breath you could thank for phytoplankton, and consider that maybe nutrients are important. And then, you know, when I put this together, I was thinking, when I first came here, I didn't think that much about Tampa Bay and the surrounding areas. Most of us are looking further offshore, wondering what's going on in the world's oceans. I don't have the time to go do those kinds of things, so I've been working more in Tampa Bay area now. But I think we've seen some events recently that I know that CMS has been involved with, and I've also been doing some work with like some folks that are working with Bob Byrne and looking at what the nutrient concentrations are in Tampa Bay, because things like phosphate are important for alkalinity measurements. Well, why would that be? Well, I love saying this to my students. Well, phosphate's the fully deprotonated conjugate base of the triprotic acid, and therefore it's a fairly strong base, right? Like I just like to watch their eyes roll around in their head before I drag them through all the mathematics of that. But phosphate is incredibly important in the area. We're the third largest phosphate producing region in the world. And I don't think, even though I was here for a long time, I didn't really think about how much phosphate was going into Tampa Bay and the nutrient cycling that was happening here inside the bay and what it meant for the West Florida shelf as well. So we're going to talk a little bit about that. Now, and then another thing that, struck me as I put this on here, I was like, yeah, it's been almost 100 years that we've known about, Redfield's ratio, that he was the first one to observe this relationship, that there's usually 16 nitrogen to every 1 phosphorus in general. So I thought that was kind of interesting. Now, don't worry. I know it's Friday. I'm a chemist. I don't want to drag you through hours of synthesis. I've done it on Friday afternoons far too many times. But I'm going to talk to you a little bit about ammonium analysis. And so to do that, I'm going to have to talk a little bit about the compounds that are used in this work. And overwhelmingly, to detect really low concentrations of ammonium, since phytoplankton usually strip it out of the surface ocean, right? Because they prefer to have ammonium. If you want to do sensitive work, most of the techniques involve fluorescence detection. Now, remember, fluorescence detection is where you strike something with some light, electrons raise up to a higher energy level, and then when they fall down, they release light at a longer wavelength, right? Because some energy has been lost. Well, most of the work uses this compound, orthophthalic dicarboxaldehyde. Well, it says dialdehyde. It goes by a number of different names depending on which way you want to write it out. But generally, this compound is going to react with ammonia after you deprotonated the ammonium. And then, depending on your reducing agent, mercaptoethanol, which was used earlier, and it would react with any primary amine. So you could take OPA, use mercaptoethanol, but then you had to do some kind of separation step, right? You had to take the seawater sample and get the ammonia gas to go to across a membrane to react with the OPA, so you could keep it separated so not all the primary amines would react. Now, I've used this chemistry for a really long time, and every time I would make the reagent, I kind of had to pray to the ammonium gods because it had a kind of unpredictable characteristic. It would take 2 days when you made the reagent up in order for it to stabilize. And sometimes it just wouldn't work. And that's not a great place to start with when you're trying to get something done. Additionally, it is kind of nasty. The mercaptoethanol is pretty nasty. Later on, we discovered that you could use sulfite instead as the reducing agent. And, well, there was one more thing about the mercaptoethanol chemistry. It would only work for maybe 24 hours to 48 hours. So you waited 24 to 48 hours, and then you only had a useful lifetime of about 24 to 48 hours. So it's pretty short-lived. Sulfite is more selective. So now we don't have to worry about doing a transfer step. So that is more elegant, right? We can do more of a direct determination. It does react to some extent with primary amines, but not very much. And I'll show you some data later that shows you like the amount that we might need to be concerned about. Now, we have 2 different excitation and emission wavelengths. So we should remember that every molecule has an absorbance maximum, right? And its characteristics are going to change depending upon how the compound is structured. These are pretty close, but they have different chemical structures. So they're going to absorb at a different region, and they're going to emit light at a different region. Now, if you look at this, right, Well, let's just step back. We got conjugated double bond systems. What do we remember about conjugated double bond systems? Nothing? Well, the one thing I think about is that whenever I see double bonds, something like this, that means that those electrons are easy to excite. Anytime you have a conjugated double bond system like this, I'm not going to drag you through like descriptions of chiral rings and all those kinds of things here, right? Whenever we have these kinds of structures, they'll fluoresce, right? Easily, readily. So when was the last time everybody was up in the club? Don't act like you've never been up in the club. Yeah, Think about what, and this is the reason why, right? You have a vodka and tonic or whatever your drink is, you're in some place that has black lights on and it's glowing purple, right? And as soon as you turn the light off, right, it's like, okay, you got to go home, can't stay here. Does it continue to fluoresce? No, it stops just like that, right? That quinine sulfate in the tonic is fluorescing. One thing that always bothered me about the mercaptoethanol chemistry is, like they said, the background fluorescence was so high. That's why you had to wait 2 days before you could use the reagent. And it starts out with that reagent is just unusable because it fluoresces like crazy. And it didn't make any sense to me because of like the back in the club example. Like you turn off the black light, it stops immediately. The lifetime of fluorescence is microseconds, right? It's not days. So another thing that's really nice about this chemistry is you make the reagent up and you can use it that day. And we'll find out that it's actually stable for months too. So it's far easier to work with. It's not as toxic and it doesn't have some of the problems that the mercaptoethanol chemistry has. Now, I'll put this slide up. Oh, Paula Cobo. There's probably only one person in the room that remembers Paula Cobo other than me. You know her, Steve? Yeah, did you? Okay, I wasn't sure. Was you here when you got good? I'm glad to hear that. Wasn't sure about that. So, got this data this is an excitation emission matrix called an EEM. And this is for coastal CDOM. And basically what you're looking at is like a topographic map of the fluorescence of CDOM. And what I've done is taken and put 2 diamonds in here that represent the excitation and emission wavelengths of those other 2 chemistries that we had here, right? These excitation and emission matrix or wavelengths. So why did I put this up here? Put this up here because of my major concern with the vast majority of new chemistries that were developed to detect low concentrations of ammonium is that they didn't account for the background fluorescence of the samples. They would give it lip service. They would say that it was present, but I never saw anybody do an actual correction for it, where they would take a sample and run it by themselves and get the background fluorescence and subtract it from the sample that they analyzed with adding all the reagents to it. It's problematic. Well, you could see from this EEM that we're not in a region that has no fluorescence, right? If it had no fluorescence, there would be no topographic like feature here. So this was for the mercaptoethanol chemistry. This emission of 425 is down over here. So it's in a region where the background fluorescence is diminished, but not zero, right? I think that's important to appreciate. So my goal is to enhance the accuracy of the ammonium chemistries. Being an analytical chemist, we answered 2 questions: how much is present and what is present. And most of my time I spent on quantifying how much of something is present. So there's really 2 different ways of doing flow analysis to do it in real time. One's flow injection analysis, where you continuously stream reagents and you inject a sample. Now, mostly I'm going to talk today about reverse flow injection, where the sample and the reagent change positions, right? So you continuously stream a sample in and then periodically inject the reagent in. This gives us 2 different characteristic patterns that we see you can think of this, it's similar to a chromatogram. It's a time series of injections. And this is, so what we have here is like injections of triplicate deionized water samples, or actually duplicate deionized water samples, then some low nutrient seawater triplicates, and then spike standards. And the same thing is true over here, where we've got duplicate deionized water, and then low nutrient seawater, which is a solvent to make standards, and then some spiked low nutrient seawater samples to calibrate the instrument. We can see that it's a very different pattern, right? And what the key here is that we get this. This is deionized water, our reagents being injected into deionized water, and then this hump here is a means of quantifying how much background fluorescence is present in each sample. And you can see that it's actually a fairly significant portion of the sample. And that ties back to that EEM that I was just showing you. Like when I first started here and I developed a technique to do detect really low concentrations of nitrite in seawater, I wasn't aware. I was a chemist. I was trained by chemists. I had no idea that there was CDOM in seawater, right? I had no idea that it would fluoresce. And I spent a couple of years developing a technique that could really detect low concentrations of nitrite. And then I took it to sea and did a comparison study with another technique that had a phase extraction. And I found that my values were always high, right? And it's like, oh, there's this problem that we have to correct for the background fluorescence if we want to do this accurately. So what I'm doing is just blowing this up for you to show you like the relative scale of what's happening here. So here we have just deionized water, and I've taken and injected the OPA reagent into it, right? We can see, now we can quantify how much signal comes just from the reagent. We saw the reagent, OPA, had a conjugated double bond system, so it's going to fluoresce. So we need to quantify that. The red here is just low nutrient seawater that's been introduced in into the system, and we're not injecting OPA into it, right? And so that shows you that this, just no active reagent is going to give you some signal. And then the orange is the combined processing of that. Now, I'm not going to drag you through all the mechanics of this kind of thing. Cheryl knows me well. She knows that like this is like my wheelhouse, is building things and plumbing things together and making things work. But in essence, we're going to take a sample or standard through these valves. You're going to have it run. We add a reagent here into the sample stream. That's going to be formaldehyde and sulfite, our reducing agent. And then periodically, we're going to have OPA fill a loop here. That's when we change the position of this valve, the OPA that's in the sample loop gets flushed into the system, and that gives us our peak. And then we run it through a heater, and then we monitor the fluorescence. So that's essentially how it works. Well, this is actually data that Hannah Hunt generated for me when she was working with me. And I guess she got 2 papers last year. She got a paper on iron working, and she's the co-author on this one as well. So she's doing all right. And I have to say this, I was really impressed with her. You all are graduate students. I don't always get quality students in undergraduate level, right? And like, she was the first one that was really like that. I was like, give her something. She never had to redo anything. This is like all first takes, which I think kind of should tell you how like this chemistry works well, right? You know, we didn't have to redo anything. That's pretty rare. Once again, we have triplicate deionized water samples, then our solvent, and then you can see the calibration curve, right? Reasonably happy with that coefficient of determination of 0.9979. And generally, I try to optimize my chemistry so that I get about 1 nanomolar, 1 millivolt signal per nanomole is really what that says, something along those lines. Generally, I find that can give me reasonable resolution and precision and accuracy. Also shooting for a really low intercept, right? This hasn't been treated at all. So that's going to give you a kind of sense of the detection limit of the system. So kind of not talk a whole lot more about how the chemistry works, just these are the figures of merit, right? The quantification of its capacities. And so it has a nice detection limit. It's not sub-nanomolar, but it's 2.3 nanomolar. Limit of quantitation. Remember that gives you kind of idea of like, you can, anything greater than that is definitely significantly different than another sample. So 7.5 nanomolar. I always love the fact that some grumpy analytical chemist was the first one to write LOL, right? That's the truth, right? Limit of linearity, right? This chemistry is good, can go up to 7,000 nanomolar or 7 micromolar. So it's pretty nice that you can have a pretty large dynamic range and a pretty decent coefficient of variation, 0.6%. Usually people are happy with like 1%, although truth be told, I'd make my analytical chemistry students get like 0.05% in order. Yeah, Steve, they have a it's a growth opportunity for them, right? So remember I told you to talk a little bit about the fact that other primary amines can react with these reagents and can give you some kind of signal. So we did an interference study with that, and we took this whole suite of different amines, and we made a 1 micromolar solution up, and we introduced that and to quantify it, and assuming like the signal that we got out of it would be kind of ammonium equivalent that you would see for that. In most instances, it's fairly significant. It's much higher than like the limited detection, but it's 1 micromolar. That's not even vaguely reasonable because you're never going to see something like that. In fact, the primary amine concentration is usually more like 50 nanomolar out in the marine environment. So if you scale that down to what you're probably going to see, it's going to be on the order of the limit of quantitation, right? And so pretty fairly certain that it's not going to be contributing significantly to the signal that we might obtain with this chemistry. I did want to kind of side note about this is like I saw a lot of folks in the literature, they would say, oh yeah, well, what they would do a different study. They would take a 1 micromolar ammonium chloride solution and add 1 micromolar primary or amines to it too as well. So it ends up being like 2 micromolar total nitrogen in the sample. And they were always like, well, sometimes we saw that the signal like reduced. I was like, yeah. Like one of the reviewers asked me about that. I was like, yeah, why? Because the functional group's changing, right? And the functional group changes because some of those compounds are reacting. You're going to shift the absorbance and maximum, which means you're going to shift the excitation maximum, and then you're going to also shift the emission maximum. It's like, yeah, and I know it's not a mystery why that's happening. That was at the end of my response to reviewers. So, you know, when I was here, I work with Kent Fanning. Some of you might have met him, but he's retired a few years ago now. But he would always tell me if I worked up something like this, I was like, that's nice, but tell me something about the ocean, right? It was never good enough for him to just like be in the lab and say, yeah, this is a great chemistry, Kent. And it's like, so we went out into Tampa Bay in June of 21. And so we probably remember what was happening in June of 21. We had this massive fish kill in the area associated with the big red tide bloom that we had in Tampa Bay. And I was fortunate to like need my example field data at that time. And so we took the bios, started in Hillsborough Bay, as you probably, I hope you know where we are on the maps here. And we cruised down in this direction, starting from the north and working our way south. And I had the biologist on top of the boat counting dead fish that we came across out in the heat. You guys are tough. You know, it's like you work in like tough conditions and with gross stuff. It's like the chemistry stayed inside in the air conditioning. But what we saw, and I do think that this is the first time that like a direct quantification of ammonification associated with deceased biota has been directly measured. And so we saw about a 33 nanomolar increase in ammonia, about the same area that we saw the largest number of dead fish in the area. So that was a kind of a nice thing to be able to do. And then I know I don't expect anybody to read all this, but I'm sure you've all had experience with reviewers. So the first paragraph was what I wrote the first time. And I thought it was like, okay, we got 30 nanomolar increase. There's about this many fish. I was putting on my like biogeochemist hat. Apparently I should have kept my analytical chemist hat back on. I said, well, if they're about 0.5 kilogram, that means you're getting about 2 nanomolar enrichment of ammonium per kilogram of decaying fish. I was like, this would be something useful for modelers. They was like, that's way too speculative. That's what they told me. So I said, okay, fine. I said, in order for you to get this kind of enrichment in that volume of water, we had to release 9.5 times 10 to the minus second kilograms of ammonia into that water to get that enrichment. One reviewer still wasn't happy with it. And he was like kind of arguing with me. He was like, well, how do you know it's the fish? I was like, not exactly, but you know, there was 1,600 tons of dead fish that had been removed from the area. I don't think it was that speculative. But then, you know, they always ask you to speculate about something else, which I always was like, really? Okay. So what do we have here? We have a technique that's useful that we can determine low concentrations of ammonia, and we can put it on a vessel so that we can basically respond really quickly. I hope in the future that we can basically get out and sample these events. So I hope that in the future we might be able to do some collaborations because we can quickly deploy this system. Everything's sitting in the lab ready to go. And I do think it is the first in situ determination of ammonium enrichments associated with fish kills. Like Cindy Heil and our group down at Moat, we're very excited to be able to share that information because we've often wondered about what those kinds of things look like. So we're going to change gears a little bit to, you know, this is kind of observations that from some little projects that I had over time. And so this project I did in association with Kim Yates and Chris Moore over the USGS. And my student worked up this data. And so we were interested in what kind of variability are associated with the changes in season in terms of nutrient fluxes from the major rivers in the Tampa Bay area. And so we studied the 4 major rivers in both the wet and the dry season. I found it kind of interesting that the wet and the dry season hadn't been defined here in the area until like 2 years ago. Don't know why. So, but this is from 2019. Now, remember when Piney Point spill was, right? It's 2021-ish in that area. We're going to come back to that in a little bit. So what did we see? Well, we went out and we sampled them both in the wet and the dry season, brought the samples back. And this is basically average of all the concentrations from all those rivers. And the standard deviations is the little bar, right? And so we were kind of interested, well, what's happening? Well, here we had the Manatee River, the Little Manatee River, the Hillsborough River, and the Alafaya River. Well, you can see in general, not in every instance, but in general, during the wet season, we're seeing, not in every instance, we see a greater amount of at least ammonium, right, being released. And phosphate is generally larger in the wet season. That shouldn't be terribly surprising, right? We've mentioned that like this is the 3rd largest phosphate producing area in the world. And so phosphate's not the limiting reactant for photosynthesis in this area, at least not in Tampa Bay. What else do we see in this data? Well, we see that the Alafaya River, probably unsurprisingly, right, it has more nutrients coming out of it. That's where the major mining region. Well, if you go out to past Riverview, anybody been out to like Boyette and Alafaya River and Alafaya River State Park out there? It's great mountain biking out there. And that's where all the old phosphate mine pits are. And that's where Mosaic is doing most of its mining operations too. And so I don't find this terribly surprising, but I had never, you know, in the 30 years that I've been here, 40 years that I've been in the Tampa Bay area, I had never like quantified it. And so it's kind of interesting to see that enrichment. So we asked the question, like, is there a significant difference between the wet and the dry season? And so I have a student run some student t-tests, right? For those of us who don't remember analytical chemistry and the statistical analysis, whenever you have, these are your t experimental values. And whenever you have the experimental value that's greater than your critical value, that means the null hypothesis fails. And if the null hypothesis fails, that means there is a significant difference. So we can see for the Manatee River, there actually is a significant difference for nitrate and nitrite, ammonium and phosphate in between the wet and the dry seasons. For Alafia River, there's not a significant difference between those two. And the proof's in the pudding by looking at the error bars, right? Those error bars overlap. And if the error bars overlap, then you're not going to have a significant difference. We do see a little bit of difference for ammonium and phosphate for the Little Manatee River. All right, so we see a bigger difference for the Manatee. We see a significant difference for ammonium and phosphate in both the Manatee River and the Little Manatee River. Now, I apologize. I thought that this talk, Cheryl sent me a text message when she saw I was giving a talk. I thought this talk was next Friday. I was like, oh, and when I looked at this figure, I go, I really wish I could make the dots a little bit bigger, change the color, but you only have so much time in the week. So this is data. This is going up the river, right? Starting from the left to the right, it's going up the river. And my student who worked on this, Nicole, she wanted to put color code each one for temperature. She was very interested in temperature for some reason. But what I want to bring your attention to is the things that jump out here is these points here and here, right? When I saw that in the data, now this is from 2019. I said, why, right? This is out in Tampa Bay now, right? These are the points out into Tampa Bay. Why is the ammonium concentration higher than what it is inside the river? The river is not the source of the ammonium concentration. Now, anybody want to hazard a guess what was happening? Where's Piney Point at? Right over here, right? Piney Point must have been leaking for far longer than we thought. And it was aberrant in the data. I was like, I don't know why that's there. At first, I thought this must have been contamination in the samples. I went back to the strip charts. I'm looking at all the data. It's like, why is that there? And it's fairly high, like 8 micromolar. You're not going to get 8 micromolar ammonium in areas. You're just not. It's really unusual. So we see that the ammonium and silica concentrations are higher than the mouth of the river for both the Manatee and the Little Manatee River. And I think I know why. Right, and it might be that the Pine Point Reservoir was leaking much earlier than we were made aware of. So, kind of highlights from this work is that the Alafia River by far has the highest concentrations of nutrients. We generally see nutrient concentrations a little bit higher in the wet season. Manatee and Little Manatee rivers have high wet season ammonia concentrations. And I think it's probably that Piney Point was leaking earlier than March 2020 when the leak above water level was detected. And then, the leak in the liner was discovered in March of 21. So who knows how long that was leaking into Tampa Bay. And I kind of, sitting here when I was driving over here, I was wondering, is this associated with declines in seagrass, more algal growth, all those kinds of things? Because we got a lot of nutrients being pumped into that area. And certainly, it's never going to be phosphate limited here. So those observations from locally, I'm going to take you back even further in time to 2004. I don't think you were in Florida then, Steve, were you? No. So I was actually out on a research expedition from the September of 2004 on the Walton Smith, doing an experiment. We were injecting sulfur hexafluoride into the West Florida shelf and watching the biogeochemical cycling of nutrients in the labeled water. But we had 3 hurricanes that crossed the pass, and we had to run for Key West at the time. All the armchair admirals were wondering what we were doing. It was like, get it back out there and work. I was like, no, they told us to go to port. You're like, you don't have an option, right? But a massive amount of rainfall was associated with these 3 hurricanes that crossed the area. And when I came back from Key West and we did another sulfur hexafluoride injection, you had to wait a couple of days before you can start sampling for sulfur hexafluoride. After you had to wait for the concentrations to come down before so it doesn't overwhelm the instrumentation. I took the waiting time to map the bolus of nutrients that had been injected on the West Florida shelf. And ever since that day, I've wondered about this, because following this injection of nutrients, what we can see here, like the nitrate plus nitrite, this bolus, right, it's 1,000 square miles, right? It's like the size of Rhode Island. It was off the West Florida shelf here, and we can see that, it's fresher water here. But I've often wondered, is this somehow related to some of the red tide events that we see? And I'll mention it to the phytoplankton ecologists, and usually they go back to like their 12-point plan or whatever it is, And I do appreciate, this is going to fuel a diatom bloom, right? But following this, we had a really long and sustained red tide bloom a few months after that. It lasted for over a year until another hurricane came through and put enough turbulence into the system that it dissipated the red tide. And so since that day, I've been wondering about how these episodic events might be impacting bloom events, or how they might be related to that. Because this is hard to sample. I just happened to be in the wrong place at the right time. And so what we've been doing recently with Cindy Hall's group down at Moat is they've been collecting samples from all these stations. And I'm going to talk mainly about the ones in Charlotte Harbor and the Caloosahatchee River today for the last part of my talk here, because these are the ones that we thought that might be the most interesting. So what we've done is taken samples throughout the year and we've analyzed them, and we've also getting the USGS tide gauge height data for Charlotte Harbor and for S79, which I'll show you in a second, which is in the Caloosahatchee River. And so what we see here, we got flow rates in blue on this y-axis, and we got nutrient concentrations here. But what we see is a pretty clear coupling between increases of nutrient flux, which is not terribly surprising. You get a lot of rain, you're going to flush any fertilizer that's on land into the system. What I did find interesting was kind of the decoupling here. Like you see, like flow rate go up, but chlorophyll didn't necessarily go up rapidly for the Charlotte Harbor area. Now this is for like September, right? Hopefully we remember what was happening in September of last year. We had a Hurricane Ian in the area. So we did see like a pulse of nutrients, but in Charlotte Harbor, we didn't see corresponding increase in chlorophyll, which is a little different than what we see down at the Caloosahatchee River at Lock S79, where we see definitely large amounts of nitrate that are following the pulses of water, but we see like a kind of co-located increase in chlorophyll there, where we have high flow rates at the same time. Probably because this is behind a dam, right? And this is being controlled. And so you're giving the phytoplankton enough time to work with the nutrients that are present. But I do think that the Charlotte Harbor area is very important. The Peace River drains into that, and we see very high concentrations of nutrients in the Peace River area in Charlotte Harbor as well. So I'm very curious to study those areas more. So a couple of highlights from that is just that we did see significant nutrient spikes during periods of high rain. And we know that Hurricane Ian hit Southwest Florida in late September, and that created a lot of flooding. And that the inflow of fresh water and the introduction of nutrients were followed by observed bloom offshore in October of 22. We just had another hurricane scare for our region, right? We did get some rain associated with that. I have one student who's studying red tides, And she's been really psyched to find red tides. And I don't know if you realize, like a few weeks ago, we did have another short-lived red tide event too, kind of just a short period of time after that last rainfall event. So I'm kind of curious to see what we might find in the future with these studies. I'm going to wrap the talk up there, and I'm happy to answer any questions that you might have about any of these kinds of things.